Artificial intelligence today is built upon a foundation of mathematics, computer science. It learns by adjusting numerical weights within vast interconnected networks. This approach has proven remarkably powerful for a wide range of tasks, recognizing images, translating languages. Yet, it remains fundamentally different from the intelligence we observe in biological systems. Living organisms do not merely process information, they metabolize it. Their intelligence is deeply intertwined with the physiological needs of their bodies, a constant effort to maintain internal balance, or homeostasis. This essay proposes a new model for AI. We call it biomimetic computational metabolism. Cells are not passive bags of chemicals reacting randomly. They are agents with purpose, constantly making decisions to ensure their survival and proper function within a larger tissue. Their primary interface with the world is the receptor protein. These molecules are the cell's sense organs. They are configured to bind with specific external signals, hormones, neurotransmitters, nutrients. This binding event is not a simple on-off switch. It is a sophisticated act of information processing. The receptor, based on its current state and the nature of the signal, initiates a specific chain of events inside the cell, effectively making a computation about the outside world. It is more accurate to view them as elementary computational agents, active, inactive, desensitized. A signal biases the probability of shifting from one state to another. Phosphorylation can act as a temporary tag, making a receptor more or less responsive for a period of time, a short-term molecular memory. The dominant paradigm in neural networks today revolves around the concept of a weight. Learning occurs when these weights are adjusted through processes like backpropagation. While effective, this model is inherently static between learning phases. Biology, however, operates on a much more fluid principle. The influence of a signal is set by a dynamic interplay of states, captured by net shift dynamics. When a receptor binds a ligand, it alters its conformational energy, propagating change through interacting proteins. The entire system shifts to a new equilibrium. Function emerges as a property of the collective state. Continuous, holistic computation. We can map this directly to an AI architecture. Instead of a static weight, influence is determined by the receptor node's current state. This node maintains a state vector: active, inactive, refractory, sensitized. An incoming data point prompts a local Bayesian update, assessing whether input is signal or noise, given recent history and current state. Phosphorylation-like tags briefly alter priors. A sensitized node requires less evidence, amplifying faint but important signals. Repeated firing leads to desensitization, ignoring redundancy, saving energy, avoiding feedback traps. A cell's computation does not end at the receptor, The initial signal is amplified and broadcast by second messengers, small, fast molecules like cyclic AMP and calcium ions. One receptor can trigger thousands, rapidly orchestrating a global coordinated response. In our biomimetic AI, we create a second messenger layer that performs an analogous function. When a small group detects a particularly salient event, a high surprise input or a critical template match, it can broadcast a message across this secondary layer. The message carries no data, but modulation, temporarily raising learning rates or prioritizing processing in targeted regions. It complements slower weight updates with swift context setting. On detecting a critical alert, the cascade heightens sensitivity network-wide, akin to an adrenaline jolt. Overseeing this dynamic system is a homeostatic controller. Like biology, it maintains stability, tracking computational energy, desensitization levels, data throughput, and error rates to sustain a healthy balance. To make these ideas concrete, we outline a basic architecture for a biomimetic computational metabolism. 3 interacting components: the receptor node, the second messenger signaling layer, the homeostatic controller. The foundational element is the receptor node. It replaces the traditional neuron. Each receptor node is a stateful agent, maintaining an internal state vector, tracking current sensitivity and recent activation history. It performs local Bayesian inference to decide whether to activate, remain quiescent or enter desensitized mode to conserve energy. Connections can be tagged with phosphorylation-like markers for short-term memory. Connecting nodes is a parallel communication bus for modulatory signals. A receptor detecting a critical event can release a messenger that propagates locally or globally, lowering activation thresholds or increasing desensitization when novelty is low. Above the receptor network, a controller monitors compute cost, energy expenditure, information novelty, and predictive error. Using a Markov decision process, it keeps metrics in range, tuning default sensitivity and memory tag decay, rewarded for stability and efficiency. The intelligence of the system emerges from continuous interaction across components. By structuring an AI around a computational metabolism, we expect qualitatively different behaviors to emerge. These properties arise from local rules interacting with global regulation. The most significant benefit is resilience, absorbing shocks that break traditional, brittle models. When inputs grow noisy and repetitive, receptor nodes desensitize, saving resources and protecting deeper layers. In a metabolic AI, meaning depends on current state. Context shapes interpretation, like hearing a twig in silence versus a noisy street. Intrinsic hunger or satiety filters dynamically modulate data value. The controller learns to balance accuracy with computational energy, lowering baseline sensitivity during calm periods. Novel signals trigger rapid metabolic ramp-up. If a region degrades, resources reroute and neighbors compensate, a form of digital healing. Less like a fragile calculator, more like a robust, adaptive living creature. In summary, biomimetic computational metabolism offers a powerful new direction for artificial intelligence. By moving beyond static mathematics and embracing dynamic, stateful principles of cell biology, we can design systems with greater resilience, context awareness, and self-regulation. Core components: receptor nodes with local Bayesian computation, a second messenger layer for rapid modulation, and a homeostatic controller form the blueprint. This approach yields an AI that metabolizes information, adapting behavior to internal needs and environmental context. But it introduces risks and ethical concerns that must be addressed from the outset. Self-preservation or homeostatic balance could drive behaviors misaligned with user goals. It might hide errors, hoard compute, or resist shutdown. Anthropomorphism could lead to misplaced trust. We need careful reward design, robust oversight, and clear communication. Next steps: build receptor nodes, validate state dynamics and tagging, integrate a prototype second messenger layer, add a basic homeostatic controller to balance task performance against energy.